Good afternoon. Hopefully I will capture your attention after lunch. I appreciate everyone's just eaten, so I don't know, halfway through I'll make a really loud noise just to wake you all up. So I'm going to be presenting a customer case study today. Unfortunately, our customer couldn't make it for personal reasons, so I'm giving the presentation on their behalf. Because they're not here, I'm not going to mention who they are, because that's not fair. They've got no control over what I say about them. But I'm going to go into quite a lot of detail as to what their setup is and how we worked with them. So first of all, I will explain who we are, though. So Alexis is the I/O profiling company. You've probably guessed we're based in the UK. And the company was originally founded to solve I/O and dependency problems in the semiconductor industry. That's my background, and I'm one of the founders of the company. But we now work across HPC and other similar sectors. We work in life sciences, cancer research, we work in automotive, oil and gas, anywhere where you care about the way you are accessing your data. And the tool that we use with the customer they'll be presenting today is a tool called Mistral. This is something that we developed with the IT department at Arm in order to protect their shared storage from users overloading the cluster with bad I/O patterns. So this is an example of the kind of job that prompted us to develop the tool, and it's very representative of the kind of job that our customer has. I'll call them customer X. It's a software build, and on this cluster, Arm has specified that users should use temporary storage, local storage for temporary files. But the user hasn't done that. You can see from this trace that lots of, can you see my mouse? Oh, you can, excellent. Lots of data is written to ARM Scratch, and nothing is written to /temp, which is where the local storage is. And so when this job is run at scale, the entire cluster slows down. And these are some of the other problems that we've seen. It's very, very easy to write too much data if you leave a debug flag on, so you're debugging something on one node or on local compute, and then when you fix the problem, you run the job at scale and the debug flag is left on. This is a problem that customer X has all the time, and it's also something that they saw all the time at Arm. The other problem is too many metadata operations. So putting open and close inside a for loop. We've seen this crash file systems when a user has done this in a very tight loop. But we've also, when we've been profiling, found this in commercial codes, actually. So not enough to actually crash the file system, but enough to have quite a detrimental impact on performance. And finally, the last example is creating too many small files. That could be part of the architecture of the application and just bad design, or it could be something that users have done naively or maliciously. We had one system integrator come to us, and they said they had a customer who deliberately created a million empty files in one directory because their metadata was on Flash and they got better performance from the metadata server. So this user deliberately did that to make their job run faster, and consequently was not allowed to use the cluster ever again, I think. No, I'm sure it was fine. But the problem that we've seen is not only creating the files, but also deleting the files and having problems when they get stored in backup as well. So that's why we developed Mistral. The main goal was to protect the storage from these kind of rogue I/O patterns, either through deliberate or accidental misuse of the file system. Ultimately, you then want to load balance the storage and get a better quality of service for individual jobs by removing these problems. And finally, we wanted a way of communicating the information back to users so that they could, so they stand a chance at actually optimizing their applications, not making these mistakes in future. And we wanted to give IT managers a good overview of what their applications were doing so that they could make good decisions about their storage architectures in future. So that's what we set out to do. And I'm going to quickly go into how Mistral works, because that's really relevant to how we did this at the customer. And then I'll move on to what the setup that we did at customer X. So Mistral sits at the application level. That means that the analytics that it can gather is very, very different from the kind of I/O patterns that you get from the analytics available to you for GPFX, for spectrum scale, or any compute node level analytics that you can gather as well. So the technology wraps up every I/O operation. Much like traditional I/O profilers out there, it works in the same way as Vampire and Darshan. It's the same underlying technology, but it's lightweight enough so you can run it on the whole cluster. So you do that by integrating with the job scheduler. Just as a quick show of hands, how many of you use Spectrum LSF? 2, 3, 4? How many of you don't? How many of you use something else? All right, so yeah, pretty similar. So I've got a little, I've got a slide at the end of how we integrated Mistral with the analytics on LSF, but you can actually do similar things with the other schedulers as well. So you just stick it on the job scheduler, and away you go. And most of the time, Mistral doesn't generate any information at all. It's very lightweight. But if a job goes over a certain limit, then it generates an alert and tells you that something's gone wrong. And these are limits that are set by you, very configurable. The idea is you set the limits high enough so that when you're running on the whole system, most jobs don't generate any information at all. But if you do something silly, such as create 1 million files, or start writing colossal amounts of data, reading colossal amounts of data, doing really, really small reads and writes, that kind of thing, then Mistral will generate an alert and tell you what's going on. So in this example, we've got an alert that says job 42, it's always job 42, exceeds 500 megabytes per second to share scratch. And the idea is that if you set these alerts on the whole system, then you can identify the rogue jobs. You can pass that information back to users, and you can find out what bad I/O patterns are overloading your storage. You can also use Mistral to throttle the I/O, but that's not something I'm going to go into too much detail today, because actually customer X didn't use that at all to protect their storage. So it's there as something that you can do as a kind of last resort, as it were. But what we found when we deployed Mistral after developing it is that although throttling the I/O seemed like a really good idea at the time, actually in practice it's way, way better to monitor and then put in place other strategies. So throttling the I/O should only be a really, really last resort, because you're slowing the job down and increasing the amount of time you're spending on the compute, you're increasing the amount of time taking up licenses and things like that. So it's really something that should be done as an absolute last resort. So now I've introduced who we are, I'm going to go into details of Customer X. So this is a Silicon Valley software startup. Actually, they've been bought. They're not a startup anymore, but they are still operating as a separate unit from their parent company. They're based down in San Jose-ish, and they've got a setup which I think a lot of you will find familiar. So they've set up their cluster to have a host leaf architecture. So their host nodes use a native spectrum scale client to communicate with their storage over InfiniBand, and each host has around 32 slots. And then their jobs, and they tend to submit jobs to the host node and then spawn a whole load of child jobs that reside on the leaf nodes. And the leaf nodes, although they do have clustered NFS, so they can access the storage, they're not supposed to. They're supposed to send data to the host node and have the host node aggregate all of that data and write to the storage. And they found that that was the best way of having a really stable network at a really large scale. They've got around 1,000 nodes in total in their compute cluster, with 8 spectrum scale filers serving them. And most of the time this works just fine, but they had 2 problems that happened on a regular basis. So the first problem was that although users are not supposed to access the storage with from the leaf nodes, actually they do all the time, and it's just bad programming, bad working practices. These are busy people, they're trying to hit a deadline, and they don't have time to read all the documentation about how they're supposed to use the system, so they quite often have the data go directly to the storage instead of being aggregated and sorted out that way. And if they hammer a particular mount point, then that can very, very easily overload one of the filers and quite seriously affect the performance of the file system. The next problem that they see a lot of the time is that the leaf nodes are aggregating data, the proper data, as it were, nicely on the host node. So that's not a problem. But someone has left the debug flag on. So this is something they saw at ARM. This is something this customer sees all the time. They're a software company, so what often happens is that one user does some work on a single node with the debug flag on, and they get something working, and then they hand over that job to testing, and then maybe half a dozen people pick up that job and then run it at scale. So it's quite a serious problem in as much as just a single user making a single mistake can actually be replicated many, many times. They don't know when these dozen engineers will run their jobs at scale, and so even if they catch one, it's difficult to catch all of them. And actually, this used to take down their system weekly. It was a colossal problem, and it used to take them hours to fix. And what they used to do was use the monitoring available to them from Spectrum Scale to see which node was causing the problem, and then they would use what they knew about the users and what they knew about the jobs to try and guess which of the job was causing a problem, and then they would go back to the user and say, look, I think you had a problem, I think we need to sort this out. And it was very, very slow. It took a long time. They managed it, but it was really taking up the time of 2 full-time people, and even then they didn't have that much data on what was going on once they worked out which job was the problem.
You have to watch your time slot. So.
Oh yes, okay. So we then were asked to come in and deploy Mistral. We deployed it across all of their production jobs, and Mistral generates an alert if the leaf node wrote to the file system. So they actually set up the alert for 1 byte. So as soon as 1 byte went from a leaf node to the file system, someone generated an alert. They also had alerts set up so if the host node started writing a lot of data, that was logged as well. And they used it for 2 use cases. The first use case was they called it my house is on fire, i.e. we're getting alerts now, let's do something sensible like killing the job or at least preventing no more of these from running. The other use case was my house is on fire, I missed it, the system is okay now, but I want to hunt down that job, find out what went on, and see what the problem was. So right now they have their own way of looking at the logs. Most of our customers actually use Grafana to visualize the information and aggregate their data. They don't. They've set up their own system. What they will be using soon is RTM, which is part of LSF, which I'll go through very briefly. But this is the kind of information they see. So they set up a rule for the mount point, GPFS. They set up read, write rules, metadata rules, and they set a limit that generates an alert. And this is the kind of information they see. So they get information about the rule, what actually happened, as well as information about the file that was last accessed, the program. So they can feed that back to users and say, we know this program at this time, while accessing this file or this area of the file system, that what was going wrong. And they found that this had a beneficial effect in several ways. One, they were able to find the rogue jobs much, much more quickly. Two, because they were able to demonstrate exactly what the problem was, exactly what was going on, the users were much more keen to actually fix the problem. And they've seen in general, when they first turned Mistral on, it was picking up rogue jobs every day. They've generally seen a massive reduction in rogue jobs detected and a massive reduction in the number of overloads on their system, because users are proactively thinking about making sure that their jobs don't overload the system, because when they do, they get proof that it's their fault. So it's a kind of has that nice sort of feedback loop. I'll just quickly go through the RTM integration, because I know only a few of you. How many people use RTM? Is there anyone here who does? No. Oh, one. OK. So very briefly, RTM is the LSF monitor. And this is just a sort of illustration of what you can do with the kind of analytics that you get. The goal was to be able to identify jobs really, really quickly. And this is a screenshot from one of the tables that you get in RTM. So Larry Adams, the engineer from IBM, has integrated this very quickly, actually, with his platform. And it gives you things like, gives you the name of the Mistral contract, the rule, the I/O type, the measurement, the event type, the threshold, the observed I/O, so everything that was going on that node. And that's per job. And then you can also get more information about who is hitting your storage at a larger level. So can give you the cluster name, the job ID, the host queue, the project user, and so on. So it's very easy and quick, even from this very, very simple view of listing the events, even without any Grafana integration or anything like that. You can see what's going on. So finally, and this is actually the more interesting part and demonstrates really why you guys, whether you use Mistral or something else, one of the open source tools or whatever, you've really, really got to profile your jobs. So Customer X don't deploy Mistral to their R&D jobs. The reason they don't do that is because the R&D jobs quite often have got extra debuggers in there as well. The debuggers expose Mistral quite often through us. If the application's seg faults or whatever, they'll see Mistral in there, and the developers don't like it. They don't like anything foreign in their environment. Now, longer term, we are looking at various solutions for them, either wrapping the clustered NFS client in Mistral technology, or potentially using something like Ganesha. Because you can wrap Mistral around Ganesha and get the same information that way. But in the short term, what they do is they guess which R&D jobs are causing problems in the old way. They tend not to be run at such a wide scale, but they can still cause problems. And then they get the user to voluntarily profile Mistral in more detail on a specific queue. So for that, they set lots and lots and lots of alerts so they can see quite detailed I/O profiling patterns. They check for things like small I/O, too much metadata, that sort of thing. And then they feed that back to users. So although it's a proactive thing, it's not something that catches jobs that are overloading the system live. It's still seen a dramatic reduction for them in jobs that overload the system, because it means that they only have to identify it once. Then it's handed over to this queue where they do the detailed I/O profiling, and then the user not only is able to fix that problem definitively because they know exactly what the problem is, so it won't recur, but also it means they've got an awareness of how that problem can arise, and so they tend not to do it again. So it's that kind of twofold improvement in the system. And this has seen a lighter load on their whole cluster as across the board, because a huge amount of the resources were being taken up by those rogue jobs. So I suppose the conclusion of my talk is profile, profile, profile all the time. It's really, really important to know what your I/O patterns are. It's very, very easy to focus on looking at the overall capacity when the overall capacity is being taken up by rogue jobs that are really not doing any work. So just make sure that all of your bandwidth, all of your capacity is taken up doing real work and not these jobs that are spinning needlessly. Protect your storage either by deploying something that can monitor live, or by doing this profiling proactively ahead of time and working with your users so that they know what's good and what's bad. And finally, think about storage in advance. So give them the tools so that they can optimize the applications for the storage and make your job easier. So, thank you very much.
Thank you, Rosemary.